So next we're going to be learning all the reactions that aldehydes and ketones can do. And there are actually quite a few, but the good news is that the reactions are all essentially exactly the same thing. The mechanism is pretty much exactly the same thing for all of them, so it's a lot of repetition. We're going to start this section 20.4, which is just going to give you like a generic overview of this nucleophilic addition reaction, which is the type of reaction that an aldehyde or ketone will do. And so we're going to go through this. It's going to explain why they react the way that they do, and then also the generic mechanism for all of these reactions. So first question says, the aldehydes and ketones are good electrophiles, and they're subject to nucleophilic attack at the carbonyl carbon. Remember, carbonyl is this guy. Does this mean that the carbonyl carbon is negative or positive? So the aldehydes and ketones are good electrophiles. That means that they love the electrons. And they're subject to nucleophilic attack. So that means that they are being attacked by something that loves a positive charge. They're being attacked by something that loves a positive charge. So this means that the carbonyl carbon is going to be carrying a positive formal charge because it's being attacked by something that loves that positive charge. So now let's try to figure out where that positive charge comes from. We're going to use resonance to explain the formal charge on the carbonyl carbon of an aldehyde or a ketone. We're going to use acetone as our example. So here's our acetone, and we're trying to explain why there's a positive formal charge on the carbonyl carbon using resonance. So let's just move those electrons away from the carbonyl carbon. See what we get. We moved the carbon-oxygen double bond electrons up onto the oxygen, which means the oxygen's going to have a negative charge now, and that carbonyl carbon, ooh, there it is. There's the positive charge. That's not the only reason. Resonance is not the only reason that the carbonyl carbon is positively charged. We can also explain it by electronegativity. We're going to use acetone again as our example. So now we're trying to understand why the carbonyl carbon is positive because of electronegativity. This one's pretty straightforward. Oxygen is more electronegative than carbon, which means that the electron density in the carbon-oxygen bond is being drawn towards the oxygen, which is going to make the oxygen partially negative, and it's going to make the carbon partially positive. So we've got both of those factors, resonance as well as electronegativity, both of them contributing to the positive nature of the carbonyl carbon. Next question says, in general, we're going to see this is true, aldehydes are more reactive than ketones. Why would that be? So in this particular reaction, we are being, our carbonyl aldehydes or ketones are being attacked at the carbonyl carbon right there. Boom. So one reason that aldehydes are going to be more reactive is that they have less steric hindrance down there at the site of reactivity. Remember that aldehydes have at least one hydrogen on the carbonyl carbon. Maybe they have two. They have at least one hydrogen, which means that this area down here, this area of reactivity, is more accessible with an aldehyde. A ketone has got two alkyl groups on the carbonyl carbon. It's going to have two R groups, which just means there's a little bit more steric hindrance. The other reason that aldehydes are more reactive than ketones, this is something that we've talked about a few times, alkyl groups. Remember, I want you to think about them as being the opposite of electronegative. They are electropositive, not a word. They are electron donors. So they push electron density away from them at something else. This means that they are pushing electron density towards the carbonyl carbon. The carbonyl carbon is kind of positive. When we push electron density towards that carbonyl carbon, it stabilizes it. Because the carbonyl carbon is positive, if we start shoving negative stuff at that positively charged carbon, it's going to stabilize that carbon and make it less positive and less reactive. Ketones have two R groups, so they're shoving electron density towards the carbonyl carbon from both the left side and the right side. It's getting extra stabilized. Aldehydes only have one R group. So that means, or maybe they have none. So that means that they only have half of the stabilization of alkyl groups as ketones. So for an aldehyde, the carbonyl carbon is going to be more positive and therefore more reactive.